Let's do some homework problems. We're going to start with number 64 in the book. I'm back to fully corporeal form, which is great. And 64 wants us to find the volume of this pyramid with the slicing method. All right. And I want to show that there really are a couple of ways of doing this. There's a lot of ways of doing this, actually. I also mentioned that it's a little easier if you flip it upside down. I'm going to flip it upside down. Let's flip this pyramid upside down. Again, you could do it right side up. If you do it right side up, it's going to be very, very similar to the problem that I did in the earlier lecture video. If you flip it upside down, again, it's 2 by 3 up here. Not a square anymore. And this height is 4 units, whatever they are. And so we're looking at volume. So for all of these, we find a cross section. And again, you can choose a horizontal or a vertical cross section. If you choose a vertical cross section, it's a little hard to see, but you're going to get a parallelogram. And that could work, but it's a little weird. So I'm going to just do another horizontal cross section, where this horizontal cross section is going to be a rectangle now, no longer a square. And we have to find this area. And that's where things get tricky. Let's call this h equals 0. Let's use y, actually. It's usually a little easier to think about for many people. So at height y, what is the area of the rectangle? And that's step 2 of that step-by-step method, and that's the hard part. So the base is going to scale based on y, and the height is also going to scale based on y. They're both linear relationships because it's a straight line for the side of the pyramid, every side of the pyramid. If it were a weird curve, then we'd have to do something like we did when we calculated the volume of a sphere. But because it's a straight line, it is just linear. And again, there's a couple of ways of modeling this. Let's use the triangle method this time. And we're going to have to use 2 triangles. One triangle for this side, and another triangle for like the front and the back, because it's different rate units. Also, you can save yourself a little bit of effort if you just notice that, okay, all of these rectangles, these are all similar rectangles, which means if we find this distance, this is always just going to be 2/3 of that other distance. So we can actually just look at one triangle. So again, if we blow up that triangle, we're saying at any height, what is this guy? Because then what we have over here is just going to be 2 of that guy, right? Given how we've set up this picture. Okay, well, at the bottom here, well, actually, let's set it up a different way. And if we look at the full size of the triangle, and then we'll look at this small yellow triangle, the full size of the triangle is a height of 4. And the bottom is 1.5, because we're looking at this dimension, half of 3 units. So we set up similar triangles. So now we're looking, what we really care about right here is, well, at any y, what is x? Well, the similar triangles, y over x is 4 over 1.5. At any height, what is x? 4x equals 1.5y. X is 3/2 y over 4. 3/2 over 4 is 3/8. So this guy over here is just going to be double that. So 3y over 4. And you could make another similar triangle using like this side. It's really hard to draw it. But this side, that sideways triangle. If you did that sideways triangle, you don't have to do this, but you could do the exact same thing with the sideways triangle, where the height is still 4, but now the base is going to be 1. Oh, wrong color. Height is still 4. Now the base at the bottom is going to be 1. Set up similar triangles for, again, y and x, like so. Or you could just say it's going to be 2/3. 2/3 of that should be 1/2 y, or y over 2. And if you set up similar triangles, again, you'd get y over x is 4 over 1. Wait a minute, what happened? So at 4x equals y, x equals 1/4 y, and again, we have to double it. That's what happens. Okay, so 2 ways of getting to that. But the point is that at any height of y, the area is just y over 2 times 3y over 4, which simplifies to 3y squared over 8. At any cross section, we have an area of 3y squared over 8. Now we just add up the infinitely many areas. From the bottom, y equals 0, to the top, y equals 4. So v equals the integral from a height of 0 to a height of 4. And here, because we flipped it upside down, we don't have to FOIL anything out. Because we flipped it upside down, our area formula is so much nicer. 3y squared over 8 dy. And we can do that on the next page. And again, you wouldn't have known that, which is why I did it both ways. But now you do. So, and there's a lot of things in math like that depending on how you set up, it can be easier or a little messier. And you just set it up, get the right answer, and then if you can notice patterns, you can try different methods. But it's not super important that you always do the easiest method. What matters is that you can use a problem-solving strategy and notice patterns and work with those. Messy is okay. Being able to handle messy problems is a very important math and important life skill. But I digress. No life rants on this video. Although take care of your teeth. Take care of your mouth. Take care of your body. Okay, no more. We can take the 3/8 out in front if we wanted. I think this makes the integral a little easier. And now we can integrate. Get 1/3 y cubed with the power rule from 0 to 4. And again, we can just keep that 1/8 out in front. 4 cubed is 64. Minus 0 cubed is 0. 64 over 8, that's 8. We get 8 units cubed. Is our volume of this pyramid. Now we should know the volume of the pyramid is 1/3 base times, or length times width times height. So it should be 1/3 2 times 3 times 4. Great, it's 8. So again, the whole idea of this problem is not that it's easier. This is one way that we can derive this formula, and it's a good logical thought process and setup for how we can generalize to more complicated things. That's the point of these kinds of problems. All right, and it's always kind of fun, I think, to show that, oh, yeah, this formula does give the same answers as this integration. And then it just really connects those concepts. Integrals are all about adding up an infinite number of infinitely tiny things. Definite integrals, anyway. Let's do another problem. Problem number 70. Draw an outline of the solid and find the volume with the slicing method. Number 70 says the base is the region under the parabola 1 minus x squared in the first quadrant. Let's draw that. 1 minus x squared in the first quadrant. So 1 minus x squared is a parabola. Let's blow this up a little bit. Have this be 1. Then that's 1. And then that's 1. The parabola looks like, pretend that goes through. And this is the point 0, 1. This is the point 1, 0. It definitely goes through that point. Okay. The base is the region under the parabola in the first quadrant. So this is the base. That region. I don't know where we're going with this. Slices perpendicular to the xy plane and parallel to the y-axis are squares. Woof. All right, this is why I do these problems, so we can give you an example of the logic. So we're supposed to draw an outline of the solid and then find the volume using the slicing method. So we're going to need to draw something with this base. All right, so this base is really not that important, all things considered. Just, again, let's try to draw this in 3 dimensions. This is some kind of parabola. And the slice is perpendicular to the xy plane. So perpendicular to this. So vertical slices. That's what it means. Perpendicular to the xy plane. In this case, if z is up, perpendicular is going to be vertical. Those vertical cross sections parallel to the y-axis are squares. Okay, so you basically take this shape. I think wait a minute. So vertical, because it's also parallel to the y-axis, so it's up and down, but parallel to the y-axis are going to be squares. How do we draw that? Or this is the base. We're going up from this base. And we have a bunch of squares. Oh yeah, it is like this. Okay, let me draw this a little differently actually. This is the base, the parabola. The top will look very similar. And then we just connect it like this. And then we have our cross sections, our rectangles. Like so. So that's why we need to tilt it, because if we draw it like that, it's not super useful. But if we tilt it, it makes it a little easier to draw. Again, we're looking at this essentially think of this base as being stretched up, stretched into 3 dimensions. And then each cross section where this is the x-axis. Let me write this out. That's the x-axis. And this is the y-axis. So vertical slices perpendicular to the y-axis are rectangles. So these are our cross sections. And we want to set this up. See if we can get through the English and say, what's the area of this cross section? And we can either do this for any x or for any y. For any x is going to be a lot easier because it's already set up in terms of x's. So let's get into it. Any x, what's the area of this cross section? Well, area is going to be length times width. Let's say this is L and this is W. Hold on. It doesn't matter what we call L and W, but let's call it this way. L and W. So L is the same, right? At any one of these cross sections, L, or the height, is all the same. Right? In this picture, it doesn't matter if we drew it there or whether we drew it over here. The height's always the same because they are rectangular cross sections. So the L is actually just always... Wait, does it tell us? It doesn't tell us what it is. All right, it's always the same, however tall this region is. However tall this region is, it's just tallness of L. But we do know this width. At any x, we know this width. Because this width right here is this. So at any x, it would have been easier to use y's. Oh well, it's fine. Well, at any x, what is this? Well, the relationship here is that at this point, y is just equal to 1 minus x squared. Oh no, that is what we want. We did set it up right. The height is 1 minus x squared. No, we didn't. The height is y. Yes, we did. The height is just y, is just the y coordinate, which is 1 minus the x coordinate squared. So what we have right here is that the area is the length, whatever that is, times the width, is 1 minus x squared. So we have our cross-sectional area. Now we integrate from the smallest x up to the biggest x. Our volume is going to be the integral from the smallest x to the biggest x, which is 1, of our area, which is L, times 1 minus x squared, dx. Now it does depend on what L is, but we can assume L is some constant. Factor it out, integrate, and get our answer. I do want to do a quick pause here. It's great for you to pause this, continue on, and see if we get the same answer. I want to... because this is almost the same as 71, right? The only difference is 71 is both first and second quadrant. And different, and here slice is perpendicular to one plane and parallel to the y-axis. Here it's perpendicular to the y-axis, so it's a little different. But again, they don't tell you. Oh, I hate it when the book does this. I'm not even gonna click on this one. I'm gonna click on a different web page, so I don't have to worry about it. I just want to make sure that they're interpreting this problem the same way I am. Oh, they're squares. Not rectangles, they're squares. Oh, I got it. So I drew my picture wrong. We know exactly what L is. This is a square. So L is the same as W. I got it. Good thing I checked. Okay, so minor adjustments. This is W, this is W, this is W. And so since it's a square, L is the same thing. And we just get again that perfect square that we can either foil. Nope, there's no either about it. We're going to foil it. Great. So I can go through this. I don't want to go through this in this video. You can definitely get this done. Integral from 0 to 1. Zero to 1 of 1 minus x squared dx is, what is that? Like 8/15. I was thinking something over 15, but I wasn't getting it. 8/15 units cubed. I see. So this picture is actually not exactly correct either. All right, since each one of these is squares, it's actually going to be shorter on the right. Up here, it is directly up, but then like it's getting shorter all the time. So it's a really kind of a hard picture to draw. Again, if you're better at drawing this stuff, that's great. Yeah, it's like something like that, where one of them is going to be up here. But then you could have another one. Let's do like another one in green, which would be like much shorter. Kind of like that. And we have the squares like that. The book, again, has good pictures, and they should be able to help you set these up. All right. And then again, we got the answer right there. Let's do the next problem. 84. Draw the region bounded by the curves and find the volume when the region's rotated about the y-axis. Y equals 3x squared. X equals 0. And y equals 3. About the y-axis. Let's not use Desmos for this one. I want to show you that what this sort of thing looks like if you do it by hand. All right, so if we have this, x equals 0, this line, y equals 3, whoa, equals 0 is this line, y equals 3 is this line, and y equals 3x squared, the parabola, that looks like this. And it's a region bounded by these curves. Okay, first off, this is kind of ambiguous. Oh, no, it doesn't. It doesn't actually matter whether we use the right region or the whole region, because if we revolve it around the axis, it's still the same solid. If you want, you could revolve this blue region, or you could revolve the whole region, and you'll have the same thing. Either way, you're going to get something that looks like this as our solid of revolution. Okay, where the radius is 1 at the top, radius is 0 at the bottom, and we got this sort of thing. We're looking at these cross sections. And again, at any height, the radius of a cross section is just the x coordinate. We know that y equals 3x squared. So what's the x coordinate? And again, you don't have to set this up with cross-sectional method. You could use the disk method to set this up. But if you use the slicing method, this is what you have. So 1/3 y equals x squared. X is plus or minus. We'll just worry about the pluses right now. 1/3 y. And again, we don't really care about x squared. We don't care about x that much. We care about x squared. Area is pi times the radius squared, where the radius is x. So it's just pi times 1/3 y, or pi over 3y is that area. So regardless of whether you use the disk method or slicing method, you get that volume is pi times the integral. Y is going from 0. Y is going up to 3 of the function in terms of y squared. Is y over 3. X squared is y over 3. Again, you could have a square root and square the square root, but you'll get this in either way. And that's our area. There it is. Or this is also the disk method. So pi over 3, we can factor that out. 0 to 3 of just y dy. Take the antiderivative. Y squared over 2. can factor out the 2 out as well. From 0 to 3, we'll get 9 minus 0. It'd be 3 pi over 2 units cubed as our answer. You can check your answer again, like on Desmos or something. Right, pi times the integral from 0 to 3 of y over 3 dy. Hopefully that is 3/2 pi. There it is. All right, let's do the last one, which is kind of a fun one, I'm hoping. We'll see what it looks like. I think it has some good trig review as well. 107. What is the volume of a bundt cake that comes from rotating y equals the sine of x? You can see sine of x like this about the y-axis from 0 to pi. So there's a little bundt cake as an example. Cross-sectional sine wave right here. Yummy. Yummy. Okay. We're revolving it around the y-axis. Oh dear, this is going to be fun. So let's get a picture. Okay, we have one picture. Let's get a two-dimensional picture. I think the two-dimensional picture will be a little easier. So here's our cross-section, right? And we're rotating it around the y-axis. And this is our region. So we're rotating this around the y-axis. We think of an upper, if it's about the x-axis, we have an upper function and a lower function, and that'd be pretty easy. But because we're rotating it about the y-axis, it's really about what's the rightmost function, and we're subtracting the leftmost function. This is the washer method. Bundt cake needs washers. The donut method, if you will. So we know that this function, this whole thing, is y equals the sine of x. And does it tell us our limits? Yeah, from 0 to pi. This is 0, this is pi. Now, here's where things get tricky. What is the red in terms of x? Because we know this volume is going to be integral over y from 0 to 1. Y is going from 0 to 1 here. Of red squared minus blue squared. But they need to be in terms of y. Right? It's f of y squared minus g of y squared. And that's the tricky part here. Because it's the same function. It's sine of x. So how do we write this in terms of y? Well, one of them will just be inverse sine. One of them will be x equals inverse sine of y, arcsine. Which one? Well, the answer is the one in the domain and range of arcsine. It's going to be the blue one. Okay, that's going to be the blue one. G of y is arcsine. Now, as soon as we do this, there's an easier way and a harder way of doing this problem. This is fine. This is straightforward. This is what I expect you to do. To be able to do is find this f of y and then subtract them and use the formula. Although you have to integrate that. You have to integrate arcsine. Wait, I don't think we did that. We had integrals that resulted in arcsine. Hold up. What's going on here? Do they have a funny answer for this? I'm right about to talk about the easier method. But the easier method is still not nice, and I want to make sure I'm not misleading you guys. Yeah, they have a real nice answer here. Okay. Around the y-axis, let me just make sure that everything's going good. Outer minus inner. But let's just play along and see what happens. Okay. So one of the ways of doing this is actually not correct. So we're just going to do the hard way. That's our blue one. So now what's the red? Well, it's symmetric about this line. What does that tell us? I believe it's just 2 minus arcsine. Oh, and I think that's maybe why it works. I don't know. No, I don't know. Why is that the case? And is that the case? And this is where Desmos really helps you. So here's my guess. My guess is that the red one is just going to be 2 minus the blue. 2 minus blue. When blue is 0. Oh, not 2 minus. It's going to be pi minus. All right, just look at a different. It's just a mirror. You have pi and you subtract the blue's x-coordinate. The blue's x-coordinate 0. And then here, it's just pi minus this blue distance. Yeah, I think that's what it is. And you can visualize this if you want on Desmos. So x equals arcsine of y. Oh. Wait, am I losing my mind? I might be losing my mind. That's not the shape I wanted at all. That's not the shape I want either. Arcsine of y. Yeah, this is fine. Because specifically we want this from y goes from 0 to 1. And then the other one, I'm saying, looks like it's going to be pi minus this arcsine of y. And again, from 0 to 1. Great. And that's the region, that's the thing, this area is what we're revolving around the y-axis. As a side note, there's a much easier way of doing this. It's called the shell method that we haven't learned yet. And sometimes I'll say, hey, the disk method's easier, the wash method's easier. And sometimes I'll say the shell method's easier. The shell method is easier here, but we don't know it yet. Okay, so let's simplify this out a little bit. Right, this is going to be pi minus g, arcsine of y. The volume is pi. Really don't know where this problem is going with the disk washer method. F squared is a little hard. We have to FOIL it out. Pi minus arcsine of y squared minus g squared, just regular arcsine of y squared, dy. And this is going to be integral from 0 to 1. Let's FOIL this out. I squared minus 2 arcsine y plus arcsine squared of y, which will cancel with this one. I'm just going to cancel it right now. I don't have to write it. So we have pi times the integral from 0 to 1 of pi squared minus 2 arcsine of y dy, and y'all cannot compute this yet. I'm pretty sure it's probably, I'm almost positive it's possible with integration by parts, but I don't think you have a tool. I don't think we covered the integral of arcsine in this class. So I think you can just use a calculator right here and hope to get to the right answer. Pi times the integral from 0 to 1 of pi squared minus 2 arcsine y dy. Let's see if that's the same answer that the book has. The book has 2 pi squared as the answer. That's not the answer. Okay, so a very simple thing missing is when I foiled, we needed a pi here in that cross multiplication, so that should be our answer. So we just edit the pi right here, and I think we should be good to go. I'm pretty confident. There it is. And again, there's a couple of ways of doing that. There is a formula for it. It's not a formula I'd ever expect you to know. I'd have you derive it with integration by parts. See, literally that's the result when it comes up there. And yeah, you get something kind of funny. You get, here, we'll pull it up for you guys if you wanted to. This is not something, you can use a calculator for this one, but it's x arc sine of x plus the square root of 1 minus x squared plus c. Again, that's not even something I would ever memorize, because if I ever had to do it as well, I would just use integration by parts, which we're waiting till chapter 3. And I guess the book's just being a little weird here. Now, if you find a way of doing this problem without integration by parts, I would love to hear it. But in the meantime, here we are. Again, we'll approximate our answer here. The book has an exact answer, but if you're using a calculator, you're going to have to approximate the answer. 19.739 units cubed. Which again, their answer was 2 pi squared. Which is the same. But you wouldn't know that if you're using a computer to approximate your answer. That's pretty much it. Let me know if you have any questions, and enjoy.